When an object is moving in a circle, one of the most basic things we might want to know about it is how fast is it going? Well, the period is the time it takes to go around a circle once, and the circumference is 2 pi r. So if speed is distance divided by time, then that's circumference divided by period. That's 2 pi r over capital T. If it's going around multiple times, say we knew it went around 27 times in 30 seconds, you could just then put in the number of times it went around and divide by the total time rather than the period. Pretty simple, right? This is called very commonly the tangential speed, sometimes the tangential velocity, sometimes the orbital velocity, sometimes the orbital speed. Speed is a better name than velocity because the velocity is constantly changing. It is going in a circle, but both are used relatively commonly. Now about that velocity change. Anything that is moving in a circle is accelerating, and this acceleration is called centripetal acceleration. Centripetal means center seeking, or toward the center. If you think about it, if you're taking an object and you're spinning it around on a string or a rope, and you let go or the string breaks, it's going to fly off tangent. That means that if it wants to go this way by itself because of inertia, but instead it's coming around this way, something is pulling it inward toward the center of the circle. You've probably heard the term centrifugal force or centrifugal acceleration. That is fictional. It's something that is not actually real in an inertial reference frame. So the tangential velocity is the result of a centripetal acceleration, which is caused by a centripetal force. It takes some knowledge of vectors to derive the equation for centripetal acceleration, so we're not going to worry about that here. You just need to know it. It's on your reference tables. Centripetal acceleration is equal to the velocity squared divided by the radius. And if Newton's second law is still true, and it is, F equals ma, and so the centripetal force is going to be mv squared over r. You might want to memorize that because it comes up a great deal. Wait a minute. What do you mean there's the force is toward the inside? I've been on an amusement park ride. I get thrown to the outside when I'm getting spun around a lot. Well, think about this. Say you're half asleep in the passenger seat of the car, and you're just kind of half dozing away, and then the driver suddenly makes a hard right. From your perspective, you get thrown against the outside of the car. You get thrown against the door. Hopefully not that much because you're wearing your seatbelt, right? But you get thrown against the door, and that to you means that you experienced a force outward. But there's no way that's what's happening. A U in motion tends to stay in motion unless acted upon by an outside force. How could the car going that way underneath you cause you to go that way? It doesn't even make any sense. What's going on is that you're trying to continue straight, okay? You're going this way, and the car door is getting in your way as you turn. So the car is actually pushing you inward. For every action, there is an equal and opposite reaction, so you are putting an outward force on the door, but you're not causing the door to go in a circle. The door is attached to the rest of the car. The door is causing you to go into a circle, and that is because of an inward directed force. Centripetal force is center seeking. Centripetal force is inward, not outward. Centrifugal force, the outward force, is fictional. We are going to be doing free body diagrams with centripetal force as well, but we're never going to put centripetal force on a free body diagram. In the previous example, the door was providing a force. That was a normal force between you and the door. If you are standing on the earth and you're going around, you've got a couple forces on you, gravity and normal force, right? You're technically going in a circle. Those forces don't quite add up to zero. I've been lying to you all year. It turns out that gravity down plus normal force up has to add up to the centripetal force of mv squared over r. Do that math and you can see why that was a reasonable lie, a reasonable detail to sweep under the rug for a while. But regardless, centripetal force never shows up on a free body diagram because it is not itself a force. Centripetal force could be caused by gravity in the case of a satellite, tension if you're spinning something on a string, the various normal forces in things if you're in a roller coaster. All sorts of different things can cause a centripetal force, but it itself is not a force if all of the forces add up to mv squared over r, tip to tail, toward the center of a circle, then you will be moving in a circle, and it is a centripetal force situation. If they do not add up to mv squared over r, then you will not be going in a circle because you do not have a centripetal force on you. So centripetal force is not its own special class of force. It's if the forces happen to sum to mv squared over r, then they are centripetal. As an example, let's look how speed bumps work. The goal of a speed bump is to keep you from driving too fast. And the way to do that is to provide you with some natural incentive. You don't want to break your car. So a speed bump is a little piece of a circle that you drive over, and if you drive over it too fast, it kicks your car in the air, and then when you come crashing down on it, it damages the bottom of your car. So if we wanted to set up a speed bump for, say, 5 miles an hour, 10 miles an hour, whatever, they're going to be different shapes, different curves. How do we determine what size curve we want for the speed? Here's how.
First, start with Newton's second law. Then realize that if you're just barely not leaving the ground, normal force is 0, so the only force acting on your tire is gravity. Set mg equal to the centripetal force MAC. Cancel the m's, that's neat, it doesn't matter what kind of car this is. And then solve for r, or solve for v, whichever one you want. Note that it doesn't matter what car it is, but if your tire's big enough, it'll just squish right over the bump and won't matter anyway, which is how monster trucks and things do it.
Another interesting application of centripetal force that got a lot of talk back in the 60s and 70s, but really fell out of favor for a long time, is using spinning space stations in order to create artificial gravity. It's not real gravity, it's something that simulates gravity. The idea is we get everybody basically in a giant amusement park ride. You create a big circular shaped space station, maybe, and then you have everybody stand on the outside as it spins. They're trying to fly off tangent, but it creates a force, and it looks like this.
We want the force to simulate gravity, so set centripetal force equal to mg. Cancel out the m's and solve for v to get how fast you're spinning. v equals the square root of rg is exactly the same as the speed bump equation, and the fact that those two things that seem so very different are so similar is a very interesting thing indeed.
Oh, one more little detail. Objects that are hit in their center of mass will get accelerated, and we have so far in this class kind of assumed that's always been the case when we're pushing or pulling something. But if you hit something off center, it will rotate. So when a bat hits a ball, the ball is hit center of mass and it is accelerated normally. But the bat is hit off center and rotates. In this case, the bat player system rotates, it slows down when it hits the ball. In the same way, if I toss a pair of scissors, those scissors are going to form a parabola around their center of mass. That'll flip and turn and spin in all sorts of ways, but overall the object center of mass just makes a parabola like we're familiar with. Another fun picture of that is this one. This is Garai Dadali, a Naples graduate who became one heck of a crazy good skier, as well as a good engineer. We'll get into all that in more detail when we talk about torque in the rotational dynamics video.